Xiani Yan, she did a biomedical engineering degree with us, finishing in her last year was 2009, and she did a Part 4 project with Paul and myself and perhaps Vijay, if I remember.
Yes,
oh, was
Vijay.
Vijay still here? I think so.
Well, he was. He
Yeah.
left right after that.
And that was on breast biomechanics. So keeping with the theme of women's health, Xiani decided to stay with soft tissue mechanics, good girl, and change or take her skills into another area in modelling childbirth. So she did a PhD with Jenny Kruger, Paul Nielsen and myself, working on how to set up 3D biomechanical models of the pelvic floor and looking at childbirth. She's going to tell us all about that anyway. And so thanks, Xiani.
Cool. Thanks everyone. Welcome to my PhD exit seminar. I won't go into too much mathematic details into it, but I do feel like the most important thing I've learned from my PhD is probably not the actual knowledge is just as important, but what I feel like I took the most from my PhD is the actual scientific way of conducting scientific research, how to think properly, how to apply my mathematical skill to a problem. And the most important thing is not to be scared by a difficult problem. Just break it up into little parts and tackle them individually. So, welcome again to my PhD exit talk on modeling childbirth. In the next 40 minutes, I'm just going to talk to you briefly about what my findings are and the different strategies that I use to model the second stage of labor. First of all, I'm going to talk about why we want to model the second stage of labor. It's quite a natural process, so the majority of the women go through it at least once in their lifetime. And apart from satisfying our curiosity, there's actually more implication than just that. This is because childbirth-induced injury occurs in 15 to 30% of the vaginal delivery, and is one of the leading risk factors that cause pelvic floor disorders, including stress incontinence and pelvic organ prolapse. It manifests itself as a partial or a complete detachment of the muscles in the pelvic floor from its pubic insertion. So at this point, we might have a few questions. First, why does childbirth affect the health of pelvic floor health? And second, why are the muscles in the pelvic floor important? The scientific term for these muscles are called the levator ulnar muscle. I sometimes call them LA muscle, just in short. I'll use those two terms interchangeably. And third is, what are the consequences of the pelvic floor muscle injury? To answer this question, we need to look at the anatomy of human pelvic floor first. Well, this is woman's anatomy. So the levator ulnar muscle, they originate from the pubic side wall. They form this semicircular path and form a sling around urethra, vagina, and rectum. This triangular opening here, we call it the levator hiatus. During the second stage of labor, the fetal head needs to go through the birth canal here. So if you imagine when a fetal head goes through the birth canal, the levator ulnar muscle that form a sling around it would initially resist the descent of the fetal head and then undergo enormous stretch to accommodate the passage of it. Once the stresses on these points are too high, levator ulnar muscle injury may occur, and sometimes when things are particularly bad, these muscles may be pulled completely off from their bony insertion. If we keep in mind that actually all the pelvic organs sit on top of this muscular shelf, it wouldn't be too difficult to imagine why stress incontinence and pelvic organ prolapse may occur once this muscular shelf is compromised. Once these are compromised, some connective tissues may still remain to partially attach some of the remaining muscle fibers back to the pelvic side bones. But the thing with connective tissue is they don't contract, and once they go through repetitive loading, they may elongate, and this triangular opening will just keep growing in size as a woman breathes, sneezes, runs, or jumps without the proper support of a contractile muscle. To put the function of the levator ani muscle into more scientific and formal terms, they regulate intra-abdominal pressure, they help with pelvic organ support, and they maintain urinary and fetal continence. Pelvic floor disorders may cause discomfort and significantly reduce a woman's quality of life. Preventive strategies are currently the research focus because surgical correction is not always effective. And to gain a better understanding on the mechanics of the second stage of labor and the development of the levator ani muscle injury, and hence the development of the pelvic organ prolapse and stress incontinence, is one of the main focus for female pelvic floor research. So bioengineers have been using biomechanical simulations to model the second stage of labor. However, there are several limitations of the existing modeling framework. First, most of the modeling framework are based on a subset of pelvic floor structures. They are anatomically incomplete. Second, there is a lack of experimental data that characterize the mechanical behavior of the pelvic floor structures. In addition, most of these models are based on the geometry of just one woman and one single head. It's really quite arbitrary. And they don't have any information on how the shape would vary in a population. So in my PhD, I aim to fill in some of the gaps and gain a better understanding on the mechanics of childbirth and hopefully to identify some risk factors of a difficult childbirth. So the goal of my thesis was to create a new modeling framework of the childbirth and use this framework to quantitatively analyze the mechanical response of the pelvic floor during a vaginal delivery. And in today's talk, I'll take you quickly through how I constructed the anatomically accurate models of the pelvic floor and fetal heads, and how I conducted the statistical shape analysis on these geometric models. Also, I talked about the construction of the biomechanical model of the childbirth, and I will take you through the roles of the pelvic floor structures and the influences of their mechanical properties on the mechanics of childbirth. I also studied the effect of shape variation of both the pelvic floor and fetal heads on the delivery force, and explored the feasibility of using statistical regression models to rapidly predict the delivery force. To create the individual specific models of the pelvic floor, I took MRI data of 28 nulliparous women. Someone else did the segmentation, but I went through and checked the segmentation. And we collected these segmentation data from these MRI images, so just combining slices of the segmentation data together. And the structures I have considered are the levator ani muscle in this pink color, the perineal body that constrains the anterior opening of the levator ani, the obturator internus that provides lateral constraint to the deformation of the levator, the external sphincter that provides caudal constraint to the opening of the levator ani during childbirth, the bony pelvis, and the pelvic joints. To conduct a statistical shape analysis, the 28 individualized models of the pelvic floor went through an iterative principal component analysis fitting procedure to ensure their point-to-point correspondence. So the term point-to-point correspondence really means that in a group of finite element models, the nodes in all of those models corresponds to the same material position anatomically. And this iterative fitting procedure was inspired by the work on femur conducted by Zhu from AVI. I won't go into the detailed mathematics of this process, but the basic idea is that we take the 26 individualized model of the pelvic floor and first conduct a principal component analysis on it and extract the principal modes of shape variation. And then the 26 individualized models of the pelvic floor were reconstructed only using the principal components and the corresponding weights selected by IKEAKI information criteria. And these PCA reconstructed models were then used as the initial estimates for the subsequent geometric fitting. And this process iterates. The intuition behind this is to create a group of models that had better point-to-point correspondence. So the intuition behind this whole iterative process is that the principal component analysis extracts the primary modes of shape variation in a sample population according to their relative appearance. And by using this dimensionality reduction approach, because we conduct IKEAKI information criteria, to only select enough mode weights to accurately represent the geometry of the pelvic floor and removing some principal components that has less importance in the sample population. So by performing this dimensionality reduction approach, what we are hoping for was that some of the individual specific features and some highly localized features would be removed so that it can achieve a better initial estimates for the final geometric fitting, because it will still be as close as possible to the final product of the geometric fitting that fits the segmentation data, but it doesn't have too much localized features that may shift the nodes arbitrarily and essentially sabotage our point-to-point correspondence that is required by an accurate principal component analysis. So once we are happy with the point-to-point correspondence, we then conduct a final principal component analysis and extract the primary modes of shape variation. And I also take these primary shape variations and study the effect of those on the delivery force. I'll talk about the findings of this later in the presentation. Due to the limited craniospatial field of view of the MRI acquisition, only the lower pelvis were included in the principal component analysis. However, the presence of the upper pelvis, including the ilium, sacrum, part of the ischium, was quite important for the specification of the boundary condition for my childbirth simulation. Therefore, it was approximated using the visible woman dataset. So the model of the upper pelvis went through a series of mathematical transformations so that the dimension of it would be consistent with the lower pelvis. And then the upper pelvis and the lower pelvis were just combined to form the final complete model of the pelvic floor. The models of the fetal head were created using a similar approach from CT scans of 28 newborn infants of less than 9 days of age. They went through this iterative principal component analysis fitting procedure to ensure their point-to-point correspondence. Over here, the yellow points are the surface of the bony plates, and these red lines are the sutures and the fontanelles. This example CT image was taken from this purple plane in the left lateral view of a fetal head. This is an example of the childbirth simulation that I've conducted. The cranial aspect of the sacrum was fixed in space because maternal vertebrae stay relatively still during the second stage of labor. The fetal head was displaced through the birth canal over a series of steps, starting from a well-flexed occiput anterior position. So that just means that the face of the fetal head is facing the back of the mother. The blue lines are the sutures and the fontanelles. To orientate you, the fetal face is where this opening is. I implemented frictionless contact constraint in the open source software, Open Symonds, and I used the software for all of my childbirth simulations. There are a lot of uncertainties in the mechanical response, in the mechanical properties of the pelvic floor structures. And unfortunately, there aren't too many experimental data. So the constitutive relations and the material parameters used in these studies were implied or derived from a very limited set of experimental data and some histological description. To test the sensitivity of these uncertain, or to test our model prediction on the variation of the material parameters, I use this sensitivity analysis approach where I conduct the childbirth simulation using varying material parameters, changing one at a time, and compare the simulation results. By doing that, we are hoping to get a better idea of the range of mechanical response we may potentially get when we are changing the numerical values of the material parameters. And also please keep in mind that these educated guess should be superseded once proper experimental data become available. And really we should be only using material parameters characterized by experimental data. In this study, for the levator inner muscle as well as external sphincter and obturator internus, so basically all the muscles in the model, I use this modified Humphrey and Ng constitutive relation. It's hyperelastic, incompressible, and as you can see, transversely isotropic material relation. And one of my senior work colleague, Shannon, she introduced this parameter alpha that represents the contribution from the muscle fiber to the elastic response of the levator island muscle. So she introduced this parameter to scale the contribution from the muscle fibers to the overall strain energy function. This phi iso, so the first term, is describing the mechanical response of the ground matrix of the LA muscle. And this is really the fiber component, well, the fiber contribution to the strain energy. A and B collectively define the response of the ground matrix, and C and D defines the mechanical response of the muscle fiber. This lambda F is the stretch ratio in the fiber direction. And the nonlinearity of the ground matrix and the fiber was indicated by the numerical value of B and D respectively. There is not any quantitative description of the LA muscle fiber organization existing in the literature. However, there are qualitative descriptions obtained from dissecting human female cadavers, and such description tells us the muscle fibers of the pelvic floor muscles are roughly parallel to each other, and they follow this course from origin to insertion. So based on this very qualitative description, the model of the pelvic floor was modified to introduce this uniform fiber field. The mechanical behavior of the perineal body was modeled by this standard isotropic exponential constitutive model. This is because anatomically, it mainly consists of intermingled muscle fiber without a predominant alignment. There aren't any experimental data on the superficial and anococcygeal ligaments that connect the posterior aspect of the external sphincter to the tip of the coccyx. So this is a structure that connects the muscle to the tip of the coccyx over here. Unfortunately, there aren't any experimental data that characterize this structure, but we did find some histological description on it. We use a Neo-Hookean constitutive relation to model the ground matrix because it's mainly composed of adipose tissue, which is fat. And we assume a linear stress-strain relationship for the elastic fiber that was embedded in this adipose tissue. And it's mainly composed of 90% elastin. So a linear relationship makes sense. And the volume fraction of the elastic fiber was indicated by this V here. A 3-parameter Mooney-Rivlin material relation were used for all the pelvic joints, including sacroiliac joints, which are the joints that connects the sacrum to the ilium, that one, the pubic symphysis that connects the two pubis together, and the sacrococcygeal ligament with sacrococcygeal symphysis, which connects the individual pieces of the coccyx and between the sacrum to the coccyx. And the material parameter for those were obtained from the literature. a standard Sim-Werner-Kirchhoff constitutive relation was assumed to model the linear small deformation of the bony pelvis. The force required for delivery can be calculated as the sum of all reaction forces from the pelvic floor. During a second stage of labor, enough force must be generated to deliver the fetus through the birth canal. So this force was generated by the combined effort of maternal bearing down and uterine contraction. When the maximum force was high, it indicates a potentially difficult childbirth, because that means that the mother just have to push really hard or giving a lot of effort to push that baby out. This is the distribution of the maximum principal stretch ratios of the LA muscle. We can see that the stress concentration is really as what we expected, is where the muscle inserts into the pubis. So when the stresses at these positions are too high, the muscles can be potentially torn off from their insertion. And this injury is clinically known as a vaginal injury. Another potential site of injury is where the caudal lateral aspect of the levator ulnar muscle inserts into the perineal body. And this is clinically known as the perineal tear. Use the modeling framework I just described. I studied the effect of pelvic floor structures on the birth mechanics. And to summarize, what I found that is that the perineal body and the pubic rami have the most significant roles in determining the mechanics of childbirth. So how I conducted this analysis was that I removed one structure at a time and compare the simulation results to the results that I have obtained using a full model. So the difference between those childbirth mechanics must be from the absence of such structure. So the perineal body affected the force required for delivery and the distribution of the maximum principal stretch ratio. And I'll talk about that a bit more later. The pubic rami affected the force required for delivery and the fetal head motion. The external sphincter, the absence of the external sphincter changes the maximum principal stretch ratio at the muscle insertion into the pubis, so the primary site of injury. But the effect was not as substantial as the first two structures, the perineal body or the pubic rami. And lastly, the coccygeal, the superficial anococcygeal ligament did not have a substantial role in the childbirth mechanics, although it did provide some constraint to the cranial caudal elongation of the levator ulni. So those two had the most significant effect. Now let's look at the effect of perineal body in childbirth mechanics a bit more. So this is the plot of the force required for delivery for the full model and the model with the perineal body removed. We can see that there is a significant reduction in the force required for delivery. This is expected because really when you are removing the perineal body, this triangular opening formed by the inferior pubic rami and the levator ulni muscle is enlarged. And also without the perineal body, so without the perineal body, the lateral aspect of the levator ulni muscle can be pushed aside laterally without any proper constraint. and that results in less resistive force from the pelvic floor. Also, the absence of the perineal body affected the distribution of the maximum principal stretch ratio. So what we can see here first is that without perineal body, there seems to be a bit more stress concentration at the caudal aspect of the levator ani muscle. And our intuition behind that was because initially, when the fetal head can come through this levator hiatus, the presence of the perineal body prevents the caudal aspect of the levator from excessive stretching, because perineal itself was taking quite a lot of stretch. And these muscles were just effectively pushed back. But without the perineal body, the caudal aspect of the levator actually takes the stretch. And this might provide some supporting evidence that a midline episiotomy, so that means cutting through the perineal body, like removing the constraint of the perineal body altogether, might lead to some injury to the external sphincter, which sits directly underneath here. But we do notice that the stress concentration of the muscle insertion into the perineal body disappears because there aren't any constraint anymore. And we suspect that it might have something to do with the clinical observation that with the episiotomy, it seems to reduce the risk of perineal tear. So the absence of the presence of the pubic rami seems to affected, oh sorry, I mistyped here. This is actually the fetal head motion. My apologies. So as you can see here, the fetal head motion have changed significantly when the pubic rami was missing from the model. So when I'm talking about pubic rami, it's really this point here. The reason why we remove the pubic rami is that apart from this model, every other childbirth model would not have this part in their modeling framework. So we really want to see what's the effect of not having it in the model. So by removing the pubic rami, the fetal head seems to just still go through the birth canal fine, but instead of following the course of the inferior pubic rami that goes towards the inferior and posterior direction, if these structures are not here, the fetal head just glides underneath the pubic symphysis and achieve fetal head crowning straight away. But with the presence of the pubic rami, it seems to be able to, it seems to force the fetal head to be pushed more towards the posterior direction. And hence that we notice the difference in the fetal head motion. So translation in the y direction means that how much it has been pushed posteriorly. With the full model, it has been pushed quite far without the inferior pubic rami. The fetal head crowning just happens as soon as it passes the point of the pubic symphysis. On a side note, I used a higher contact stiffness for my childbirth simulation to achieve a better numerical stability when I was conducting simulation for the pubic rami. And this is because of the choice of the constraint, the choice of the method that I used to apply the contact constraint is called penalty method. So the contact pressure was maintained by the contact penetration. So the higher the contact pressure, the higher the overlap needs to be to maintain such high pressure. And when pubic rami is not there anymore, the contact area between the fetal head and the anterior pubis is really just this little bit here, which is not much at all. And to maintain such a high contact pressure, you need quite a lot of penetration. And that unfortunately causes numerical instability. And hence, I increased the contact stiffness for this case specifically. So this is just a comparison between the model with the pubic rami removed and the full model. And also we found that without the pubic rami, a model could significantly underestimate the force required for delivery. And the intuition behind that is because the fetal head does not need to be displaced posteriorly so much, hence the coccyx does not need to rotate as much as it would when the full pubic rami was there. To rotate a coccyx, keep in mind that the coccyx was attached to the sacrum by this very stiff sacrococcygeal symphysis. So to rotate the coccyx a bit further, you effectively have to deform these pieces of ligament further, and hence contributing to this difference in the delivery force. And also, without the pubic rami, this area of the levator hiatus is enlarged and hence less resistive force from the pelvic floor. I also studied the effect of material parameters of the pelvic floor structure on the childbirth mechanics. I found that an increase in the muscle nonlinearity using these mainly exponential form of constitutive relation it resulted in a more homogeneous distribution of the maximum principal stretch ratios. And also because of the way that the constitutive relation was set up, changing the nonlinearity of the ground matrix would affect the response in the fiber and the cross fiber direction, like to affect both of them. So an increased degree of ground matrix nonlinearity had a stronger influence than the degree of nonlinearity of the fiber. I also found that increased muscle anisotropy gave rise to an increase in the overall maximum principal stretch ratio. And that's also because the way we are changing the muscle anisotropy, keep in mind that this alpha is an indication of the muscle anisotropy. So when you increase the alpha and maintaining the elastic response in the fiber direction the same, that means this 1 minus alpha, so the contribution from the ground matrix, is reduced. Because in the cross fiber direction, there aren't any fiber reinforcement. That means the relative resistance to stretch in the cross fiber direction is less, and hence the increased overall maximum principal stretch ratio. We found that changing material parameters of other pelvic floor structures, including the pelvic joints, the anococcygeal ligaments, and perineal body, within the physiological range of variation did not have a significant effect on the childbirth mechanics. I also studied the effect of shape variation on the delivery force using the PCA-derived models that encapsulate the principal shape variation of the pelvic floor and the fetal head in the population. So put that into a language that human can understand. It just means that I generate the main model of the pelvic floor, taking the principal component, take the principal components of the shape analysis, take the standard deviation of the individual principal components and reconstruct a model one standard deviation above and below the mean model for the first 5 principal components that encapsulate 96% of shape variation. And when I was looking at the effect of the shape variation of the pelvic floor on delivery force, I used the mean model of the fetal head and vice versa. The primary factors, the primary shape variation of the pelvic floor that contribute to a change in delivery force include the area of the levator hiatus. That's quite straightforward because if this triangular opening is smaller, the muscles need to go through a lot more stretch and hence more resistive force. And also a reduction in the subpubic angle. That just means that when this angle is more acute, so when the 2 pieces of bones are closer together, that's effectively closing down the area of the levator hiatus and give rise to a rise in the delivery force. And then a more upward tilting coccyx. Because if it's tilting this way a lot more, that means during the second stage of labor, it needs to be pushed back a lot further. And the primary shape variation of the fetal head that increased the delivery force was really a no-brainer. It's the size of the head, whereas other shape change, like other local shape change, they might have an effect, but it's not nearly as significant as the overall size of the fetal head. To make these models more useful in a clinical setting, I also explored the feasibility of using partial least square regression models to taking the geometry of ideally it should be both the maternal pelvis and the fetal head, because the overall force would be dependent on both the passage and the passenger. But in this study, I only had time to look at the effect on the passenger, which is the geometry of the fetal head. Considering the difficulty of obtaining a full finite element geometry description of the fetal head, we also look at just using some reduced parameter. This biometric parameter including biparietal diameter and fetal head circumference that are routinely measured in antenatal checkups. And the response variable are the delivery force predicted by the finite element models. So what I did is to generate the training data is to conduct individual simulations using the subject-specific fetal head and the mean model of the pelvic floor. And this generates the ground truths for the regression model. And we use a linear and a quadratic interrelation for the partial least square regression model. I won't go into too much details into this because we are running out of time, I realized. But basically what we did here is to try to quantify the quality of the partial least square regression model. Because we have such a limited availability of data, only 28 sets of observations, we don't have the luxury of dividing it into a training set and testing set. So we use this standard cross-validation approach called leave-one-out analysis, where you put away a set of input and output and fit a model on the remaining 27 sets of observations, and then get a prediction for the one that has been excluded. And then you compare the results of the prediction and the ground truth. So basically a smaller normalized error means that, and then you repeat the process for all 28 observations. And you get an average of some sort to indicate the quality of the partial least square regression model. So on this graph specifically, a tighter distribution means that it's a better predictability. And we can see that the finite element geometry as inputs to the partial least square regression model give, in general, a better prediction to the delivery force. And this is expected because although the biometric parameters capture the primary shape change in the fetal head, it's not really a comprehensive description of the localized features of the fetal head that might have contributed to the change of the delivery force. So to summarize what I've done in my PhD, I've created this anatomically accurate models of the finite element of the pelvic floor and the fetal head, and conducted statistical shape analysis on these geometric models. I created a new modeling framework of childbirth and used this childbirth framework to look at the role of pelvic floor structures and their mechanical behaviors on the childbirth mechanics. I also look at the effect of shape variation of both the pelvic floor and the fetal head on the delivery force, and explored the feasibility of using statistical regression models to rapidly generate predictions of the finite element simulation results. And I would like to acknowledge my supervisors, which are all here today, Martin, Paul, and Jenny, for their continuous and non-failing encouragement and guidance throughout my long PhD. And they never lost confidence in me, even though when I was trying to give up, towards the end, I was, I can't do this anymore. Like, those three keep encouraging me through the most difficult parts, and I really appreciate their guidance and really the unfailing encouragement. Thank you.
Thanks. And before the questions, I just want to make a few comments on really this novel contribution aspect. So what Nancy has done really, really well throughout her entire thesis is really to get to the nuts and bolts of some really, really tough problems, particularly to do with contact mechanics. There's a whole bunch of real challenges to do with implementation of the contact mechanics in our code. She was able to get right to the crux of that and to work through a whole bunch of the difficult challenges. But as was evident in her talk today, she never lost sight of the applications of the work and the clinical implications. So you'll always be able to take that from the nuts and bolts bioengineering all the way to the kind of clinical applications, and was always kept on track really by Jeannie here with all of the terminology, the language, and the application area. You never lost sight of that. The other thing I want to say around this is that out of Xiani's PhD, she's had 2 high-quality journal publications and really good journals. She's had 3 book chapters and good publications as well. And I think you presented at 4 international conferences. I seem to remember Singapore, Spain, Scotland, and the States. So, yeah. And the sort of theme with all the S's, you're now working for Soul Machines. And
really, the only reason I could get from that job is from a continuous discussion with Martin of how to solve a nonlinear system, how to maintain the stability of my optimizer, and how to deal with ill-conditioned linear matrix. It's really all the stuff I learned from my PhD at time, which I thought, I spent so much time, maybe I could have just take someone else's work and just focus on the application. But really, it's a blessing in disguise. It's
a lot of problems.
Really, yes.
Yeah. So, questions, please. Go.
Hi. Very good talk. It's actually about the alpha parameter.
Yes.
So you take a proportionality, and I suppose that proportionality doesn't mean 70% per se. If you really want a percentage, won't you divide and normalize it with the true strain energy again, and then but the division of the normalization was not there.
Yes, I completely see what you mean. This alpha parameter was actually just quite an arbitrary parameter that we introduced just to scale the relative proportion from the fibers to the ground matrix contribution. And really, because of the lack of experimental data, we have actually no idea how much actual contribution in terms of the stress and strain response between the fiber and the ground matrix. So this alpha was there to give us a rough idea. By changing it, it gives us a rough idea of how the pelvic floor muscles would respond. But unless you have a solid set of experimental data that tells you, okay, at this particular strain, the stress in the cross fiber direction should be 30% of the fiber direction, then really it doesn't really matter that much that this alpha means. It's just a parameter that we introduced to change the individual contributions from those two, from the ground matrix and the fiber, actually. So it's more of an empirical study rather than solid experimental data-based, unfortunately.
If you had an opportunity to sort of carry on research in this area, what would you do?
To carry on research, actually, I have been thinking about it because one of the biggest issues I had in my PhD was the difficulty of navigating through the difficult landscape of finding that global minimum when fetal head rotation was present. So we did try quite a few different methods. Initially, we thought maybe the way we linearized the contact stiffness was unable to navigate through the difficult landscape of that numerical problem. But we tried different kinds of strategies, and none of these actually gave us any promising results reaching that global minimum when fetal head rotation was enabled. So if I could continue in the research, I think I would really try to tackle this problem of when you have a particular difficult numerical space to navigate through. Is there a better solution method that could help us to just go down that descending gradient to find the global minimum? I guess it's a difficult problem for many years, and lots of research has been put into it. But if I had an opportunity, I would like to drill down on that issue a bit more.
Harry, do you have a question? Yeah.
So in one of the graphs, you have force that increases up to about 28 or so newtons force. So I was wondering if you change when you do the CPCA and change the shape.
Yes.
So how much did that force change by much for different shapes?
Yes.
What is that?
Yeah. So for that's a very good question actually. We did look at how much one standard deviation of the shape change of the pelvic floor and the fetal head would have on the delivery force. And we found that by changing just one standard deviation of the female pelvic floor in the primary direction, that is the very first component, I recall that it changed by around 20 to 30%, which is really quite significant considering it's just one standard deviation. And imagine if someone with a particular unfortunate geometry of the pelvic floor. It could be a few standard deviation from just the mean average woman. And really that could double the delivery force. That means she has to generate twice as much force as a woman would normally generate, and that's really a big ask for a pregnant lady.
Okay, well, we should call that a day. I just want you to join with me, and I know I speak on behalf of Paul and Jenny as well, as we, this stage of a PhD is really the end. You know, the handing of the books into the library is just a part of a thing along the way, but we're absolutely delighted in everything that you've done. It's been an absolutely fantastic journey working with you, Xiani, and we are delighted to present to you Dr. Yan. So thank you very much.
Thank you, thank you. Thank you, everyone.
Please stay around and help Xiani celebrate with some food and some drink.